Hi everyone, I'm going to talk to you today about section 3.9 in your book, and that's derivative of exponential and log functions. Start off, I'm going to find the derivative of e to the x kind of the easy way. I'm going to graph e to the x, and then we're going to look at its derivative here. So here is e to the x being drawn, and then the derivative of e to the x drawn in a lighter color, but it looks to be going exactly on top of e to the x. So that was super duper easy to figure out. The derivative of e to the x is e to the x. Woohoo! Love it. Okay, and we've been working with the chain rule. So remember, the derivative of e to something more complicated than x would still be itself, but you would have to times it by the derivative of that inner function. All right, let's try a couple of these. The derivative of e to the 2x, well, we just said the basic pattern for the derivative of e to the x is it's itself times the derivative of that inner function. Derivative of 2x is 2. And you'd see this written in your book answers and on AP exams as that. All right, let's try another one. I think before I even start taking the derivative, I would rewrite this as a power function so that I don't mess up my chain rule. I'm going to start with the outer function, which is going to be the taking something to the half power. And let's take that derivative. 1/2, inner function unchanged, drop it down a power, times the derivative of that inner function. So the derivative of e to the 3x is itself times 3. And the derivative of 3 is 0. So I think we're home free here. And this would be just a fine answer. I'm assuming you could use your Algebra 2 skills to clean it up if you had to match an answer on a multiple choice. All right, so let's take a look here at another function. It is an exponential function, but it's not base e. And I'm just going to graph 2 to the x and its derivative so we can see what they look like. And there goes 2 to the x. And whatever the derivative of 2 to the x is, it looks like it's starting to graph right now. And it's interesting. It doesn't look like it's exactly the same as 2 to the x, but it really does look pretty darn close. So let's try graphing another exponential function and its derivative. Let's do 5 to the x and its derivative. Its derivative is graphing right now. Doesn't look like it's exactly the same either. Okay, so let's go back here. Yeah, so it looks once again like the derivative of 5 to the x is very close to 5 to the x, but it's not exactly the same. So if we think about, it looked like 2 to the x, that, very similar as 5 to the x and its derivative were very similar. It just looked like, in these cases, one was steeper than the other. And if you remember from your Algebra 1 training, that when we put a constant multiple in front of a curve, it changes the steepness. And that's kind of what we're going to do here. We're going to say that the derivative of any base exponential function will be itself, but we're going to need a little adjustment factor to change the steepness. And that adjustment factor is always going to be whatever the natural log of this base is. And we're going to go ahead and, if we had something more complicated, the derivative of a to the u would be itself times the adjustment factor. And then we'd have to go back and take the derivative of that inner function. All right. And we can try one here. Let's go ahead and take the derivative of 2 to the x. It would be itself times an adjustment factor. A little change of steepness, and it would be the natural log of 2. Now, the cool thing is that actually we can use that to justify our e to the x also. The derivative of e to the x should be itself times an adjustment factor, which would be the natural log of whatever base this is. And we remember the natural log of e is 1. So once again, we kind of confirm what we just thought and graphically, hey, yeah, they look the same. All right, let's look at finding the derivative of the natural log. So we're going to approach this much like we did yesterday, yesterday or earlier today, depending on when you're watching the videos, when we were talking about using some implicit differentiation. If I knew the derivative of the natural log of x, I'd be done right now. Okay, but I don't. So we're going to go through a process, and once we get the derivative of the natural log of x, we're going to remember it. Okay, it's not that hard to remember. So I'm going to go ahead and change forms here. And I'm doing that, changing back to exponential form, because I know what the derivative of x with respect to x is. It's 1. And I know what the derivative of e to the any power is because we just talked about it. Derivative of e to the anything is itself, and then we'll take times the derivative of that inner function. And now I can go ahead and solve. And much like the derivatives of the inverse trig functions, we're going to make a substitution right here. X is e to the y, so we can make a nice substitution and get a very simple derivative for the natural log of x. And by the same count, if that was a little more complicated than plain old x, we do 1 over u, and remember to take the derivative of that inner function. So let's try one. Derivative of, okay, so we would need, we're over here, something more complicated than an x. We could identify our u as being x cubed, and our du, our u prime, derivative u with respect to x, as being 3x squared. And we can just plug stuff in, right? The derivative of natural log of anything is the 1 over the anything times the derivative of the anything. And that can absolutely be simplified and reduced to something much simpler, which is absolutely fine and dandy for us. Okay, let's get cooking on this derivative of logs that aren't natural logs, right? Logs with other bases. And I'm not sure how much you remember about your change of base formulas when you were in Algebra 2, but if we have log base ax, we can rewrite that. If you hadn't discovered that log of any base button in your calculator, your teacher might have made you do something like this. And these are equivalent, and we have those buttons readily in the front of our calculator. You don't have to search for them, and your teacher doesn't have to hide them from you. So we're going to use that identity that these are the same. And instead of taking the log of this, derivative of this log function, we're just going to take the derivative of this. If they're truly equal, their derivative should be equal also. Now this is kind of cool. We're going to use some of our laws here for derivatives, our rules. This ln a, that's a constant, so we can take that out. Which makes our life really, really easy. Because I can actually do this calculus. The derivative of natural log of x is 1 over x. And kind of similarly, when we were taking the derivative of e to the x and then we were taking the derivative of a to the x, we had an adjustment factor. That's really very same thing of what we're doing here. The adjustment factor for the exponential functions was a multiple of ln a. And this is going to be very similar. We're going to have derivative of the natural log, and then we're going to have this adjustment factor, but it's going to be in the denominator. And that is the derivative of logs of other bases. And if we had something a little more complicated, we would get 1 over u times the adjustment factor. And we have to remember to go back and take the derivative of u. And let's give this a try. So this one looks a little more complicated than a plain old x. So the derivative of log base anything of something, x squared we'll say, is going to be 1 over the something times the adjustment factor, and our base is 5. And then we just have to remember to go back and take the derivative of the inner function. And that would simplify. We could also simplify that to match an answer if we really had to. On a free response, you can feel free to leave it just like that. All right, folks, that's all I've got.